Well, thanks for all of you guys for joining. I hope that you're going to enjoy this. It'll be a lot less math and a lot more fun, I think, than my last presentation. I know so many of you struggled with that one, and so there is the only thing in here is arithmetic and geometry. So that should be pretty straightforward for everybody. So the title of this one is Calibrating the Unknown and How Science Builds on Itself. And what it's about is how science ladders on itself. So in the beginning, whether you're talking about the size of the Earth or distance to the stars or whatever, it's always beginning with uncertainty, right? People don't know things. Their measurements are crude and often myth-laden. So for example, way back when, Aristotle was kind of the scientist of his century, and he was full of shit. He thought the Earth was the center of the universe. He thought that women had fewer teeth than men, and he didn't even check, right? He just assumed it and said it. And then he thought the universe was static, and he relied on observation occasionally rather than experimentation. So, but some people, we'll see many of them on this presentation, did rely on experimentation and careful measurements starting a long time ago. So we're going to start back in 260 BC, where Eratosthenes used nothing more than sticks and shadows to calculate the Earth's circumference, which was like totally mind-blowing. Centuries later, Oli noticed timing irregularities in the eclipses of Jupiter's moon and figured out how fast light travels. A couple of hundred years later, Henry Cavendish used a torsion balance to measure the gravitational constant. And from that, he was able to calculate the Earth's mass. In Bessel, some of you may know Bessel from Bessel functions for the mathematicians among us. He was also making careful astronomical measurements and was able, for the first time, to calculate the distance to a star, which is like mind-blowing, right? I mean, 1838. What was going on in 1838? That was pre-Civil War. Lewis and Clark hadn't finished too many years earlier than that. I mean, these are a long freaking time ago. And these people were able to accomplish a lot of amazing things. And then from their beginnings, science kind of laddered up on their first steps, stood on their shoulders to get more and more accurate measurements. So we're going to kind of take a look, see how those stories unfolded, and I think you'll enjoy these stories. So the first one is Eratosthenes, the librarian of Alexandria, 22 freaking centuries ago. And he learned an amazing fact. At noon on the summer solstice, the sun shone straight down in the bottom of a well, no shadows, which is kind of a unique thing. And he thought, I can make the most of this. Where he lived in Alexandria, on the summer solstice, things were still casting a small shadow. And if the Earth were flat, it wouldn't do that. And so this difference implies curvature. So, you can throw out all the crap about, Columbus and sails disappearing over the horizon and everything. That was in 1500. This was 17 centuries earlier than that, right? So all that childhood crap, throw it out the window. So he applied some basic geometry. At noon on the solstice, he measured the angle of a shadow cast by a vertical stick, a gnomon, like you would see in a sundial. You can see that here in home in Alexandria. And the angle was about 7.2 degrees, or 1/50th of a circle. And so now all he needed was the distance between the well where he lived. And he used some caravan travel records, which are not terribly accurate, of course, of about 5,000 stadia. So you simply multiply that by 50 and you just obtain 250,000 stadia, which, if you convert to our modern kilometers, comes to within a few percent of the true circumference value of the Earth, which is like astounding, right? A stick in the ground and a distance measurement between two cities, and you get the Earth's circumference. You can see here I have a diagram of kind of how this geometry all works out. But this is just the first measurement of the Earth's size. Of course, it has been refined later in many more ways. In the 8th century, so 1,000 years later, this Arabian guy ordered teams of astronomers to measure the length of a meridian arc by actually doing surveying, right? So they didn't count on, reports from Camelback to get to an arc measurement, and so they were able to get much more closer. Now, at this point, another 1,000 years passes, and people have been tweaking on that measurement. And the question is no longer how big is the Earth, but what is its shape? It turns out it's not a sphere. Do I need to do something with that? I can't see all the controls. No.
With what sphere?
No,
I just heard.
No
I just heard.
It's just
Okay.
no take it.
All right. So Isaac Newton, the guy that figured out the mathematics behind gravity, had predicted, because of those forces, that Earth was kind of a flattened sphere. And so to test this, the French geodesic mission to the equator back in 1735 was set off to make more accurate measurements, both towards the equator and towards the pole. Now, this one towards the equator was led by none other than Maupertuis. Who remembers who Maupertuis was? Anybody? His name from the very last Feed Your Head that I did. No, he was the guy that thought that nature was economical, right? And then it was Euler that took his ideas and took them further. So that's actually kind of an interesting thing, in that these ancient scientists, right? They didn't just do one thing. They did many things, right? I mean, these guys were into math and geography. Aristophanes, right? He was a mathematician and a geographer and a poet and an astronomer and even a music theorist, right? All these guys were polymaths. Anyway, so these two missions determined the accurate shape of the Earth, because, as you can see up here to the top right, the equatorial diameter is greater than the polar diameter by a fair amount, just about 56 kilometers. So anyway, so then finally we come to today, and of course we have many fancy instruments, and with laser ranging and GPS constellations and gravity mapping missions like GRACE, we can measure all of this stuff within centimeter scale precision. And that reveals that it's not just an oblate spheroid, but it's constantly changing, right? All these measurements before were kind of assuming that it was constant. It's not constant, right? The surface is rising and sinking, and mass is redistributing as ice melts and oceans shift in tectonic plates. So what began with a stick and a shadow in Alexandria is now a real-time measurement. So that's our first example of how science ladders on itself. Before we go on, is there any questions about that? And are any of you familiar with any of these stories, like Eratosthenes? No?
There are many people over there that believes the Earth is flat, Paul.
Yes, I know. It's
I think Nick is one of them.
No,
Well,
we're like the giant tortoise, okay?
That's right. It's tortoises all the way down, right? All right, the next one is the speed of light, c. For most of antiquity, light was assumed to travel instantaneously, and that was a pretty fair assumption, because it's so bloody fast that you really can't observe the speed like you might observe the speed of a horse or a train or anything like that. And so, but still, 10 centuries ago, the Ole Rumor was looking through his telescope and studying the eclipses of a moon of Jupiter, Io. And all these guys were careful note takers. You can see these plots of his data here. And he noticed that the timing of the eclipses of Io by Jupiter drifted systematically, depending on whether the Earth was moving forward or away from the Earth. So from this, he was able to infer that light takes a finite amount of time, right, to cross the additional distance. And he made an estimate that it would take about 22 minutes to cross the diameter of Earth's orbit. That's not quite right. It's probably closer to 18, but he was really darn close given the time. So, but at this point, it was finally confirmed. Light is not, the speed is finite, bloody fast, but finite. So then a terrestrial measurement was made here by a guy whose name I can't even believe, right? Hippolyte Fizeau measured the speed of light using an experimental setup, right? So this is moving from just, looking through telescopes and making careful time measurements to actually setting up an experiment deliberately to measure the speed of light. So he set up a mirror about 8 kilometers away on a mountaintop, and he set up this toothed wheel. And the idea here is the light would pass between the gaps of the teeth of this wheel with 720 teeth, turns out. And so the speed of the wheel was increased until at 12.5 revolutions per second, the returning light hit the next tooth and couldn't be seen, right? So now he has, he's able to, at 25.2 rotations per second, the light was again visible. And so from this, you can very straightforwardly calculate what the speed of light was. And he did so within about 5% now of today's accepted value, which was remarkable for still a pre-Civil War measurement. And so, yes, was there a question?
Yeah. I'm not going to try to butcher the name, so I'm going to call him Hippo and Romer.
Yeah, just call him Fizeau. Yeah.
Fizeau. What, if anything, in the nature of the name of this figurehead, did Fizeau or Hippo use from old Romer to build on when going from like theoretical to, hey, here's an actual experiment to improve to 5% of accepted value?
Yeah. So I think what we can say is that he didn't use the same methods that Ole did, but Ole put down the first stake in the ground. He determined that light had a finite speed, and he made a first guess at it. So Fizeau took that concept and said, okay, it's been 200 years. I can probably do better, and was able to set up an experiment to deliberately do it. Remember, Ole actually kind of accidentally stumbled upon it, right? He just noticed the timing of the eclipses were off. He wasn't deliberately going out to measure the speed of light. He sort of discovered that it was finite by accident. And then he made an estimate from it.
And do you know if Fizeau was doing this based on like excitement and what he grew up loving to do, or love of the game, as they say, or like was there a specific problem that he was trying to solve to improve?
Well, like many people, he, of all of the people we're going to be looking at here, he was a polymath, right? He studied many different things. In fact, he was also involved in the discovery of the Doppler effect, right? Which you're familiar with, right? The pitch of a train changing as it approaches and goes away from you. So that was, he made measurements in that. And so, he was basically, a scientist that, unlike Aristotle, is constantly making measurements of the world around him. And so once Romer showed the way and said, hey, light speed is finite, he came up with an experimental solution or an experimental setup that was able to make an accurate measurement, which is really difficult, right? I mean, he had to get huge distances, right, 8 kilometers away to get a distance, enough of a time delay with this toothed wheel spinning at 12 revolutions a second to do that. So he didn't build directly on it, but he took the original concept. Hey, light speed is finite. What the hell is it? Does that answer your question?
It does. It answers both questions. But I'm not going to lie to you, I didn't know what the Doppler effect was.
No, really?
Anything that has the word effect afterwards, I probably don't know.
Okay.
Or don't remember.
Later in this presentation, we'll have something that actually builds on that concept.
Okay.
So we'll talk about that even more later. So finally, the Michelson-Morley, what was the other guy's name? Oops, sorry. Anyway, Michelson and Morley in the late 20s or early 20s was also trying to make a more accurate measurement. Now, the funny thing about him was he actually wasn't trying to actually figure out the exact speed of light. What he was trying to do was to figure out whether or not ether exists. Now, this is a really funny concept for us in the modern days, but centuries ago, back in the early 1900s and before, it was thought that the whole universe was filled with this substance ether, and the ether carried waves, right, like light waves and stuff. They didn't think light could transmit through nothing, and so if there was an ether, then light, the speed of light should be different in different directions. So he would need a very accurate way of measuring the speed of light, and then he would measure it, in different directions, as relative to the way the Earth was moving around the sun, right? So kind of facing it into the rotation in 90 degrees from it, etc. And he expected to see a difference. And so he needed an extremely accurate way of measuring the speed of light to test this different hypothesis. But we're just going with his speed of light. And so he had a spinning mirror. Now we've gone from a toothed wheel to a spinning mirror, but this is all in the lab, right? This is all just right in a basement where they set this up, where they've got a telescope and a source, and they were able to, by some simple math here, as you can see, I won't go through it all, but it's all here for you guys to review later. But basically, as the mirror is rotated, the light returning to it won't be incident at an angle of 45 degrees and so won't enter the telescope. So you can see that the split view of the source and the rotating reflection will only line up during the proper angles. Now, this was an extremely accurate measurement, and he was able to obtain a value of 2.99775. The exact value is 2.9979. So he did that to within a 10,000th, right? So now we have a remarkably accurate view back in, just post World War II of the speed of light. And based on this, he actually prior to World War I, he became the first American to receive a Nobel Prize in any science, honored for his optical precision instruments, which is pretty cool. All right, so let's go to a different story. The Earth's mass. And at first glance, it seems like measuring the Earth's mass is an impossible task, right? It's like, where's my scale? Where's my lever? Where am I going to stand to measure the Earth's mass, especially since it's moving? So the methodology here is to build on Newton's equation of gravity, wherein the force of gravity is equal to this gravitational constant times the product of the two masses divided by the distance between them squared. And so if you know G, and if you know R squared, the distance between you and the center of the Earth, your mass falls away because it doesn't even make any difference here, right? It's your mass is so much smaller. So then we would have an equation in which we could, you can see here is that mass of the Earth is simply GR squared if the mass of the Earth is much greater than your mass. So it's very simple, but it's quite amazing. He basically had this rod that was suspended by a thin wire, and at the end of these rods were a couple of masses that weighed a few pounds each. And then he brought even larger spheres closer to those, and the mutual attraction of the smaller and the larger spheres made the bar twist. And so you can actually calculate then from this torque and how far they've moved, how much gravitational attraction there actually was, and calculate G. And so he actually, to measure this tiny angular deflection, which is minuscule, he used a telescope aimed at a scale reflected in a mirror. So you can basically, if you think about this, if you put a mirror on the rod, and reflect a light off it. If you look at the reflection very far away, 10, 20, 30 feet, it'll actually be easier to see how far it moved. And he was able to determine the torque and therefore the force. And this is really tiny force. This is about 10 millionth of an ounce, which is freaking tiny. And so, but then his result was actually quite accurate, within 1%. And so given this equation, we can actually calculate the mass of the Earth. So a twisted wire and some lead spheres, and he gave us the mass of the Earth, which is a very big number, 250 years ago. And this governs every orbit, every satellite, every tidal interaction. This number is key to an awful lot of stuff. So that was the first time that it was done, right? And that was more than 2 centuries ago. So, of course, once we have a method, we can improve on it. Now, here's where Mitch's question kind of comes in, that he used the same method. And this guy, Boyes, used the same technique, a torsion balance, but he made it a lot more accurate. Used quartz fibers, and the whole thing was set up in a vacuum and everything, and so he got much more close. But there are finally today there's an even more accurate view of both the mass and how the mass density of Earth changes. NASA and the German Aerospace Center launched the GRACE mission, and that's basically 2 satellites here, as you can see. They're traveling in tandem in the same orbit, and as the leading satellite passes over a region of slightly stronger gravity, it accelerates slightly, increasing the distance to the trailing satellite. And then as the trailing satellite comes up, then it too will accelerate, and their separation comes back down to what it was. And so by measuring these changes down to micrometers, using lasers, of course, we can map tiny variations in the gravitational field. So not only do we know what the hell it weighs, but we can see how its density varies over the whole planet. And this feeds into all the other sciences, right? And groundwater and earthquakes and ice sheets. All of this stuff kind of feeds into the variable density of Earth in various places. So we went from the torsion balance back in 1798, a couple of weights on a string, to a couple of satellites chasing themselves and measuring the variations in Earth gravity. So pretty cool path there as science ladders itself up and makes ever more accurate measurements, and then gets additional insights, right? I mean, the people that were originally measuring the mass of the Earth, had no idea that its mass or its density might be variable. They were just trying to get a number for the whole thing. So we were able to, science over the last few centuries, able to refine those measurements. So now we come to my favorite one, which is measuring the distance to the stars. And before I kind of dive into how he did this, I want to first ask, does everybody here understand the idea of parallax? Who doesn't understand the idea of parallax? Anybody?
I don't. Parallax?
Okay. All right. So you can demonstrate this to yourself by holding a finger out at your arm's length and closing one eye at a time. And you'll see the finger move against the background. So everybody go ahead and do that. You see how it moves, right? That is called parallax. And basically, this is how people judge distances to things. Our baseline is the distance between our 2 eyes, right? And so each eye sees something slightly differently. And so from that, we calculate, the brain does it all on its own, but calculates how far away things are. Okay. Is everybody now clear on parallax?
Yeah.
Okay.
Thanks.
Yeah. It's fancy word for something pretty simple, and something that, hey, there was the most easy experimental setup of all, right? Your finger at your arm's length. So Friedrich Bessel, who was also a famous mathematician, was using his telescope and measured the shift in a position of 61 Cygni, which is the name of a star, as Earth moved from one side of its orbit to the other. So if you look down here on this diagram, here's our sun, and here's January and July, right? So the opposite ends of our movement around the sun. So in January, we are looking at the star, and we see this angle here, and then as we move back here, we see it from this angle. And so here's kind of the picture that he saw here. You can see A as the star. You can see these stars are the background stars, and A shifts from one side to the other as the Earth moves around. So we know our baseline, right? Our baseline is the diameter of the Earth's orbit, right? 186,000 or a million miles, right? And so from that, simple geometry, we calculated a distance of 10.5 light years. Now, I say simple, but the distance, this angle was less than a third of an arc second. That's 0.000092 degrees. That gives you an idea, back in 1838, using equipment that looks like this, of how accurately these guys are able to make measurements and then make calculations that are rather remarkable. So for the first time in history, one star, we've been able to measure the distance to one star. This is just totally awesome. Now, a little side note here. So this parallax was 0.31 arc seconds. Now, you may or may not be familiar with how people divide up degrees, but you can divide degrees into decimal degrees, like 31.23 degrees, or you can do minutes and seconds, right? So there's 61 minutes in a, 60 minutes in a degree. There's 60 seconds in a minute. And so we're talking here about arc seconds, right? So this is a fraction of a way small fraction of a degree. This distance, this parallax arc second, became a measurement, a distance measurement for stars, right? A measure of distance. So you might say a star is 5 parsecs away. That would mean it is 5 arc seconds of parallax given our Earth's diameter. So that's that you may have heard this, but now we use light years because they're a lot easier. But parsecs was kind of the original distance measurement for stars. So this is the first rung in the ladder of measuring distance to stars, which is, I think, really remarkable. Right? This was 1838. That pre-Civil War times. Andrew Jackson was president. It was a long time ago, and people were making these kind of measurements. So next, how do we keep building on this? This one is really cool. So there was this gal, Henrietta Leavitt, who was an American astronomer, and she was hired by Edward Pickering to measure and catalog the brightness of stars. Basically, they were women weren't allowed to actually operate telescopes. The typical thing for women in science, they had a lot to battle against. But they gave her a bunch of plates, photographic plates, to measure and catalog the brightness of stars. And while she was doing that, she noticed a precise relationship between their pulsation period and their luminosity. That's pretty amazing, right? So their brightness would change with time, and how much it would change would depend upon how bright they were. That's a pretty cool thing. And so she made a whole bunch of measurements and came up with these constants, these type of stars that exhibit this variability called Cepheid variables. I actually made measurements on these myself when I was at NASA 100 million years ago. Anyway, so the key now is how do we calibrate this, right? The luminosity and the absolute brightness, right? And so this is where the laddering really shows up. She was able to measure some stars that were close enough to use parallax and then calibrate her luminosity distance. And so now she was able to say, okay, well, if the period is this, then it's this far away. So that's remarkable, right? You're able to say, okay, here's how bright it is, and here's how fast it's pulsing. Then I can tell you exactly how far away it was, and that was based on the prior work, with the parallax. So this is about one piece of science leveraging on another, and we're about to do it again. Now this was pretty cool because this extended our reach from tens of light years to millions. Now you couldn't measure parallax in millions, but now that we have the Stafford variables, we can measure millions of light years. Now we can measure stars, distances in other galaxies. Huge step, right? Finally, we are using cosmology, the redshift, to measure distances even farther away. Now I'm going to take a moment to pause here and talk about what Mitch was talking about before, which was the Doppler effect. So the Doppler effect is, right, let's just say there's the classic, train that's approaching you, and the sound of the the pitch of the sound of the train increases as it's approaching you. Its speed increases the speed of sound, and so that decreases the distance between the wavelengths of the sound. And then as it passes you, the speed of the train is subtracted from the speed of sound. And so now the pitch all of a sudden goes down, like, right? You've all heard that. Well, the same thing happens with light, right? And this chart over here to the right shows this effect. So these are light spectra, and these little black lines are absorption lines. So what that means is that in a star's spectra, if you took a spectrograph of a star, there would be a line, say this one here, for iron, right? And this is where the atomic structure of iron absorbs a particular exact wavelength. And you can actually pick out various lines to see, the oxygen line and the hydrogen line, etc. Now, what was noticed by those just prior to Edwin Hubble, that stars that were farther away, actually, these lines didn't appear at the same place. They didn't appear at the same wavelength. They were shifted towards the longer wavelengths, towards the red part of the spectrum. So we knew this was still iron, but it's moved. And the farther away the star was, the farther the iron line moved. And so what we can say here is that these shifts in spectral lines are due to these stars moving away from us because they're shifted to the red, longer wavelength. Now, what Edwin Hubble did, and you'll recognize Hubble from Hubble telescope, is he connected Stafford variables to the redshift. And so using his period luminosity, he calculated distances with these redshifts to spiral nebulae that were beyond our own galaxy. And so he published this velocity distance relationship, which is basically the redshift, and demonstrated a roughly linear relationship. So now we have a new ruler that can go as far as we can see anything, right? It's look at any star and take its spectrum, look at what its redshift is, and now it can tell you how far away it is. And so that's the remarkable last step here, that using parallax to Cephids to redshift, we can now discover how far stars are away to the billions of light years, which is like freaking mind-blowing. So that's the last example that I had. Oops, I have one more slide here. So this is sort of a big cosmological picture of this. So we have in the middle here, we have the sun and the earth, and looking at parallax on very, very close stars. And then we calibrate that with the closest Cephids. And then we have the Cephid ruler here, which expanded our reach to millions of light years. And then we took those and we looked at the redshift, light redshifted, and extended our ruler to billions of light years. This is kind of a neat graphic I found, which kind of illustrates that concept. So once again, science building on itself, using something as simple as geometry, right? Just parallax, to careful observation, to connecting different types of observations, the Cepheid variability to light redshift, and now we have a ruler that stretches to the beginning of the universe. So that's it. We began 22 centuries ago with a shadow in Alexandria and Eratosthenes, and we advanced 18 centuries to where a timing a moon revealed that light speed is not instantaneous, and we were able to eventually measure it. From a twisting wire, we weighed the Earth, and another century passed, and we were able to measure our universe, how big it is and how fast it's expanding. I threw up this picture here, which was Carl Sagan's favorite picture, the pale blue dot. And this is Earth here from 6 billion kilometers away. And I just put this in here for a perspective, because this whole story that we've just looked at, from measuring, the Earth's size, the Earth's gravity, how far away the stars are and everything, we begin to understand our place in the universe, which is a tiny place. But we, from careful measurements and extensions into larger, previously inaccessible domains, are able to refine our understanding of the universe, which is a wonderful kind of thing to do. So that's the end of my presentation. I hope that this leaves you with kind of a sense of wonder and the possibilities of what you can do with elegant reasoning from simple data, sticks and shadows, rods and spheres, and how science works. It's cumulative. It builds on itself. And so hope that you enjoyed our little journey here on Friday morning.
Thanks, Paul. It was great. You gave us a great conversation for this weekend. And also, it impresses me how this guy's curiosity led to that. I don't know who was the first person to think, oh, let's measure the mass of the Earth. For me, it's mind-blowing.
Yeah, but these guys did with such really quite primitive but elegant measurement methods, right? I mean, spinning wheels, right? And light bouncing off a mirror on a mountain. I mean, it's not like the modern, lasers and this and that, but they were able to accomplish remarkable things. So it's a very cool story.
I'm gonna ask it to Christina, my wife, to do the test. I love it.
But remember the name, Matheus. It's the parallax.
It's
parallax. There you go.
Yeah.
Parallax.
Parallax.
Yep.
Parallax.
I my question of all this is, the first guy, why? Why? Like today, I get it. We use it for loads of things, building spaceships, calculating the rate of cancer acceleration. But why did the first guy do it, and why did the second guy do it? There's a point where we get why, but before that, it's just why.
Right. Well,
nothing else to do.
These guys. Today scientists are super specialized, right? You've got guys that study biology and guys that study geography and guys that study, chemistry and physics and stuff. They're all siloed in their specialties, right? And the reason for that is it's almost impossible to become, a polyglot amongst all the sciences now, right? Our body of knowledge is too large. But back in Eratosthenes' time, or Cassini, or Fizeau, or all these guys, they didn't just stick with one thing, right? I mean, Eratosthenes, the earliest of our guys, right? He was a mathematician, a geographer, a poet, an astronomer, and a music theorist. I mean, he studied everything because he was curious about the world around him. And, you think about our buddy, what was his name? Maupertuis, right? From our last discussion, right? On math to understand the universe, right? He had this theory, right? About how nature was economical. And then people started building on that. People have had this immense curiosity about the world around them, to look up at You know, they didn't want to be a caveman looking up at the stars and thinking it was gods. They wanted to understand what was really going on. So they measured these stars. They figured out how far away they were, how massive they were, figured out, you know, their redshift and, you know, all of these things. We have a curiosity about the not just the world, but the universe around us. And all of these scientists that, you know, from before the 20th and 21st centuries knew everything there was to know. And they were dedicated to building on that knowledge. And now it's pretty much impossible to know everything about everything. But those guys, you know, had just this immense and beautiful curiosity about their place in the universe. Our pale blue dot. So that's what I had. I hope you enjoyed that as hopefully a good Friday afternoon beer chat, you know, later on. But
Yeah, sure.
Yeah.